Most folks know that you can find your latitude at sea using a sextant, but most have no idea how this works. The sextant is really nothing more than a fancy protractor designed to measure the angle between two lines of sight from the observer. It does not measure the length of those lines, nor the linear distance between the endpoints. The angle it measures between the polar reference and the horizontal plane is the observer's latitude. Let's try an example to see how this works. Let's say our observer is near the 34th parallel. We'll illustrate this with a spherical section at the great circle defined by the North Pole and the observer's position. The sextant will be measuring the angle between the observer's horizontal plane and the polar star, so let's add the observer's horizontal. When the observer is close to the surface, the observer's horizontal plane is pretty close to the plane of the horizon. In practice, some minor adjustments are made to account for this difference in the interest of precision, but we'll just keep it simple for now by assuming that there is no difference and accept a couple of arc seconds of error. For convenience, we'll show the observer's vertical, which by definition is 90 degrees to the horizontal plane. We don't need this, but it might help explain what we are actually measuring. Finally, we'll provide the observer's line of sight to Polaris and the angle measured between the star and the horizon. This angle is the observer's latitude. This method has proven to be an effective means of determining one's latitude by sailors navigating the oceans for hundreds of years before LORAN and GPS were even thought of. This method can be used anywhere between the pole and the equator, although the sextant typically only measures 60 degrees of arc. Let's see how changing the observer's latitude changes the measured angle. Let's set the whole thing in motion and see how this works. Starting with the observer at the 34th parallel, notice the angle between the observer's line of sight to Polaris and his horizontal plane is 34 degrees. As the observer moves closer to the North Pole, the angle between the horizontal and the star increases. Eventually, the angle becomes 90 degrees at the North Pole. As the observer moves south, the angle between the star and the horizontal decreases. Eventually, the angle becomes 0 at the equator. If we go just a bit further, the observer's line of sight to Polaris is eclipsed by the Earth. When we head north again, we can stop anywhere within the quadrant, take a sighting, and thus determine what latitude we are at. So, what do we do when we can't see the horizon clearly? Suppose the horizon is obscured by fog or terrain or refraction. For example, in a plane at 40,000 feet, the horizon can be difficult to see even on a clear night. Can we still measure an angle from Polaris to determine our latitude? As it turns out, we can. A device called a bubble sextant allows us to determine our vertical. From this, we can infer our horizontal, measure the angle to a reference star like Polaris, and thus determine our latitude. Let's see how this works. The bubble sextant uses a spirit level to establish the observer's vertical. The observer's horizontal plane is perpendicular to this line by definition. Once we know the observer's vertical, we can base an angular measurement from it. For example, the line of sight to Polaris might be 66 degrees from the observer's vertical. The angle to the horizon would then be the geometric complement, which would be 24 degrees in this case. This angle is the observer's latitude. When the observer is at the 34th parallel, the bubble sextant will actually measure a 56-degree angle between the observer's vertical and his line of sight to Polaris. The measurement the sextant will show is the angle between the line of sight to the star and the inferred horizontal plane, in this case, 34 degrees. Now let's put this into action. As the observer moves north, the angle measured decreases until the observer reaches the North Pole, where the measured angle becomes 0. As the observer moves south, the angle size increases until the observer reaches the equator, at which point the angle measures 90 degrees. The observer can move anywhere between the North Pole and the equator, take a measurement, and determine the latitude. It's really that simple. So, what angle is the sextant actually measuring, and what has this got to do with latitude? The latitude is the measure of the angle between the equator and the observer from the axis of rotation. So we need to find two lines of sight that represent this angle. Let's see how we find these lines of sight for the sextant to measure the angle between. We want this angle, but what if we can't get two lines of sight in order to measure it? Since corresponding angles created by a line traversing a pair of parallel lines are equivalent, we can add a parallel horizontal and measure the angle it creates instead. But we can't really get a line of sight for the parallel horizontal because we lack a fixed point of reference. We could take a line of sight perpendicular to the horizontal and measure the angle to the perpendicular of the intersecting line. This gives us intersecting right angles with a common vertex and thus a common complementary angle. So the angle C will be the same as angle B. We want angle A, but angle B is equivalent to A, and angle C is equivalent to B. So angle C is also equivalent to angle A. This final angle is composed of two direct lines of sight, the observer's horizontal plane and the observer's line of sight to Polaris. This observable angle is equivalent to the angle we are looking for, the one that gives us our latitude. Therefore, what the sextant is really measuring is the difference between the observer's vertical orientation and what it would be at the equator. I hope you enjoyed this quick tutorial on the physics of measuring latitude with a sextant. If you did, hit the like button. Leave a comment if you have any questions or thoughts on the topic. Be sure to subscribe and tap the bell to get notifications of new videos when they come out. I thank you for watching and recommend you stay sharp out there.